2016, Bob Junks, who had a collaboration with the Federal University of Viçosa in Minas Gerais State in Brazil, suggested that they should have a workshop, training workshop on subsoil constraints. And I was also invited to take part in that. So it was principally for PhD and postdoc fellows at that university. And it was really driven by Bob because he had done a lot of research around the world, in Australia and many other countries, including tropical countries, Thailand, Malaysia, Indonesia, and Brazil, and was very aware of the similarities between the deeply weathered soils in Brazil and Australia, and thought it was something that they needed to get onto. And based on the fact that in Australia there'd been a couple of decades of research on subsoil constraints, he thought it was opportune to try and bring this to the attention of Brazilian scientists. And we had the workshop, and afterwards we decided to try and publish a book. So that's the effort, many years coming. It really is a Brazil-Australia joint venture, although we're going to have a short talk from one of the authors who's actually from Thailand. The Federal University of Viçosa and Minas Gerais and Murdoch have an MOU. So we now have a partnership, and we're offering joint PhD degrees. So this is a long-standing collaboration that we've had between the two universities. And we're expecting to get a PhD student under that program shortly to come and work with us for a year. Photograph there is from the small town of Mariana, which is has a lot of colonial Portuguese architecture. Very sweet town. It's very close to one of the places where they had one of those major mine tailings disasters a number of years back. But it's one of those memorable things about travelling that it was a Sunday. We were going out on a visit. It was a beautiful day. We walked up the hill, beautiful church, and coming out of it was this wonderful music with the padre or the pastor chanting and the congregation responding. It was absolutely one of those memorable times of travel. And the photograph on the right, anyone recognise that? Not in Brazil, it's near Norcia. So that's the closest we come to Latin architecture in WA. So 16 chapters, and just over half of them were collaborations between Australian and Brazilian authors, and the rest either had all Brazilian or all Australian authors. And quite a number of them are written by authors from Murdoch and SoilsWest. And today, Wendy is going to give a short talk about her chapter, and Teogenes Senna is going to give a short talk about her chapter. Interesting thing in writing this book and the introductory and final chapters that Teo and myself led, we saw this paper by Yost and Hardnink, in which they had done analysis of prominent soils journals, and over 1,100 papers that had been published in those journals from 1989 to 2019. And 73% of those soils papers didn't even mention the depth of soil that they were investigating. And in the remainder, 27 centimetre depth was the average for those studies. So you'd have to say that in the literature, we don't give a lot of prominence to subsoils. And this book, the last book on subsoil constraints was in 1994. And there's a lot been learned since then. This book is intended to try and pull together and update our understanding about subsoil constraints, and really to bring it to the attention of soil scientists, agronomists, and hopefully to inspire a new generation of researchers to pay more attention to subsoils. So obviously I'm not going to go through the whole book today. I really just want to pull out some highlights, some things that to me were quite significant, or things that I learned in the process of editing the book. The thing that is worth noting is that if you do a Google search on subsoil constraints, most of what comes up is Australian work. A lot of it from GRDC investment from the 1990s through to the present day. So some of the old hands in the audience, people like Steve at the end might say, well, we know a lot of that stuff, and that's probably true, because from an Australian perspective, we've actually invested a lot in learning about subsoils and how to manage them. And so in some respects, the book is more for people elsewhere in the world who could learn from this and be guided in their research on subsoils from the work that's been done in Australia. The definition of what's a subsoil is not precise, and in the end, we came up with an operational definition of the subsoil. Essentially, that part of the root zone below where we normally sample soils for analysis. So if you like, it's the part of the root zone about which we're most ignorant. And of course, that will vary depending on where you are in the world. So most of the soil sampling in Australia has been 10 centimetres. In many other parts, in fact, most other parts of the world, it's deeper than that. It might go to 15, 20, 25, or even 30 centimetres. So what we call subsoil in Australia is part of what they routinely sample in many other parts of the world. It approximates to the A1 horizon and soil profile descriptions, but of course in dryland environments where the A1 horizon is very shallow, that's not true. We used to think of the subsoil as below the plough layer, but with the spread of no-till agriculture to now over 210 million hectares globally, there's a lot of land that is no longer tilled, and so that definition doesn't hold either. Some people refer to the subsurface as a synonym of subsoil, but that's the definition that we've tried to adhere to in the book, but as I say, it's not a precise definition by any means. One of the important chapters in this book was written, led by Professor Carlos Schaefer, and Carlos did a sabbatical with Bob Dukes in WA, and he and Bob had worked for a number of years on investigating soils. And this chapter focuses particularly on deep regoliths, and mostly focusing on Brazil. Large part of the Brazilian landmass, like the southwest of Western Australia, is a very ancient shield that's been geologically stable for millions of years, and therefore has these very extreme depths of weathering. There are parts of Minas Gerais where they've measured weathering depths to 250 metres. Most of these deeply weathered regoliths are in tropical zones, but you also find them in some higher latitude locations, and often this is related to paleoclimates, because you only get these deeply weathered regoliths in stable landscapes that haven't had high rates of erosion, and that means that they've existed as a regolith for a long period of time, possibly through many different climatic shifts. And that's true of many of these deeply weathered regoliths in non-tropical environments such as southern Australia. So in terms of where would this book be relevant, certainly large parts of tropical world. But there are also these other places where they have deep soils and deeply weathered regoliths where what we're presenting in this book should have some relevance also. The deeply weathered regoliths, as I mentioned, often have polycyclic origins where there's been changes in climate and biota. So the deeply weathered regoliths of southwest Australia are considered to be Eocene in age, and then during the drying of the Miocene period, you've got induration of a lot of iron aluminium oxides. So you're talking about a landscape that's got possibly a 30 million year history to it. And likewise in Brazil, there is these very ancient regoliths that have gone through many cycles of climatic change. Carlos draws attention to the important role of biota in the formation of these regoliths. In Brazil, particularly relating to the role of ants and termites in modifying the upper part of that regolith so that you get a 2 to 3 metre depth of soil material that's been thoroughly homogenised and mixed by termites and ants, creating stable structures, altering the availability of nutrients and the porosity and the hydrology and the accumulation of organic matter. And of course, some of that work on biota and deeply weathered regoliths was done by Bernie Dell at Murdoch. Published this classic paper in 1983, where they were able to explore root penetration in our deeply weathered regoliths in the Jarrah forest down to 40 metres or so. That obviously has significance in terms of carbon, which we'll talk about shortly. There's another aspect of these deeply weathered regoliths that really hasn't penetrated widely into the international literature, and that's what's called the phytotherium concept that Bill Verboom and John Pate in Western Australia conceptualised and published. And their argument is that vegetation over a long period of time alters pedogenic processes, leading to different soil profiles under the same climate. And they draw attention particularly to in the southwest of Western Australia, where you can have side-by-side Proteaceae dominant taxa, Banksias and the like, sitting over deeply weathered soils with a lot of iron aluminium oxides in them. And then there's almost a line in the sand. And on the other side, you've got mallee vegetation with sodic subsoils. And the traditional view would have been that the vegetation is there because the soils are different. But their argument is that the vegetation is what changed the soils and caused those differences in soils. So that's a concept which I think is quite revolutionary, open to contest, and it just needs somebody to pose the null hypothesis and find an exception to it, and the whole concept might disappear. But I think there's great potential or possibilities for people to look at this concept in other parts of the world where we've got these deeply weathered regoliths. We've got deeply weathered regoliths. There can be carbon all the way through those profiles, and Richard Harper's and colleagues have published on some of this work. And they've found that in these profiles that are up to 40 metres deep, that there's much more carbon below 50 centimetres depth in these regoliths than there is above. And yet most of our carbon accounting is based on the shallow surface layers of carbon. Concentrations are very low, but if you add up the total stock, it can be very large. So at this point, I'd like to see if we can get online Podgeny. who's a lecturer at the Untitled Chapter University in Thailand. She completed her PhD at Murdoch, working with Richard Harper and colleagues on this question of deep carbon. And she was the senior author of one of the chapters. So if we can get her online, we invite her to say a few words about that particular chapter.
Thank you, Professor Dale. Can you hear me?
Yes.
Okay. Hi, everyone. I would like to talk about the chapter 14 about the deep soil carbon, the characteristic and measurement with particular bearing on kyolitic profile. Yes, written by me and Bernie Darrow, David Henry, and Richard Harper. So the soil carbon storage is seen as a major greenhouse gas emission action. However, this is the mainly concern about with what is happening in the top method of soil. This chapter is a part of a study of soil carbon stored to deep of 30 meters. The carbon stored in deep soil are the great interest, not only to understand how they can contribute the greenhouse gas emission, but also how they respond to climate change. Well, this chapter we summarize the possible sources of deep soil carbon and the available methodology to study it and the location of deep soil profile in the world, as you can see in the picture. So, sorry.
Oh, she muted herself.
Hey, Podgeny, you're on mute at the moment. If you just hit unmute, I think we missed about the last 30 seconds.
All right.
Perfect.
Okay.
Yeah, we can hear you now.
Okay. We then examine the case of land use change on deep soil carbon store in the southwestern Australia. So the picture show the road cut at Mandarin. So you can see it's about the 20-meter high. When you look closely to the picture, you can see the fragile root fragment and the stain around it. So this is the main. I think this is the main source of carbon in deep soil of Western Australia. So we hope this chapter will give the reader an overview of deep soil carbon, but well, our concern more there is a little known about this important soil carbon store. We hope to see much work focused on this in the future. Thank you very much.
Thank you very much. Really appreciate you coming online and telling us a little bit about your chapter. One of the big gaps in terms of subsoil constraints globally is that they're not really mapped. There are estimates of total area of acid soils, for example, and saline soils, but really don't have accurate mapping globally to understand where these constraints exist and how large the areas affected are. And that's obviously a constraint because it means we don't know how much effort we should be devoting or investing in trying to understand those constraints. There are natural constraints, and they're probably easier to map, but there are also induced constraints, and trying to update our historic soil map to reflect the change in soil properties, pH, compaction and the like, which can be altered under land management, is one of the constraints for mapping. There are some good examples of regional scale mapping of subsoil constraints in WA. DPIRD has a very good handle on the distribution of a range of subsoil constraints. There's recently a paper published in Germany where they were able to take historic soil survey data and then update it with current management to come up with an estimate of subsoil constraints. And in their particular study, it was compaction that was the main issue that they found. But digital soil mapping is probably the way that we're going to have to go in terms of trying to take the legacy soil survey data that we have and update it as necessary with induced soil constraints from management. There's also in-field variation in constraints. And as we know in Western Australia, those constraints can vary quite markedly. And so there's no substitute for that in-field observation and learning exercise. Across Australia, there have been many methodologies developed for that type of in-field study and understanding of subsoil constraints, such as Jeremy Lemon here, who's well known to many of you, worked in DPIRD for many years and had a great style of being able to get into the hole and talk farmers through what's actually visible there and how that affects the relevance of particular subsoil amelioration techniques to that particular environment. Topsoil management obviously has been the focus of soil science for generations, and rightly so. That's where most of the roots are. Most of our technologies can be easily applied in topsoil. However, topsoil management is not sufficient. And it's illustrated in this study here by Brendan Scott and colleagues, where they've shown that the response of wheat grain yield to topsoil pH varies substantially depending on the subsoil pH. So in this particular study, as the subsoil pH dropped from 5.3 to 4.7, the response to topsoil line was pretty much the same. But once the subsoil dropped to 4.4 and 4.1, you're getting strong responses, but you never get to the same level of yield as with the high pH in the subsoil. So this is an illustration of how simply focusing on the topsoil means that there's a lot of potential being lost or not being tapped. The next question is, where are roots? Because, of course, alleviating subsoil constraints is only relevant if the roots are able to grow there, and different species have different distribution of roots. Most roots of most plants are in the upper 10 to 20 centimetres, but almost all plant species have roots that will go substantially deeper, particularly for trees and herbaceous plants. And that's led many to argue that one of the ways forward here is to look at deep-rooted plant species as a potential to exploit these subsoil reserves. And of course, the ability of roots to extract water is one of the critical properties that we need to understand. So it's about the water holding characteristic of each of those layers and where the roots are, the effective root depth. And in a lot of our research, we tend, when we're interested in roots, we tend to focus on how deep the roots grow. But it's more about the residence of those roots in different depths that is going to drive the effectiveness of them in taking up water and nutrients. And the trend towards shorter duration varieties means that roots don't reside at depth for the same length of time as long duration varieties. And there's also some opportunities to look at changing the structure of deep roots by identifying varieties that are able to produce more erenchyma in the cortex. And that enables the roots to function with less respiratory cost. And that's an opportunity to grow more roots, grow more biomass with less energy cost. So at this stage, I'm going to ask Wendy, who's been a research fellow in SoilsWest and the land management group for a number of years, and led one of the chapters on water acquisition. So over to you, Wendy, to say a few words about your chapter.
Thanks, everyone. So this chapter was written with Steve Milroy. So he helped a great deal with this chapter in conceptualising and reviewing a lot of the literature on looking at water acquisition by roots from the subsoils. And so we started by looking at mostly the physical constraints. So we reviewed some of the physical subsoil constraints in terms of root development and function. Some of those are very similar to what you would find in surface soils in terms of mechanical resistance, aeration, temperature, water, etc. And then we looked at the main components that influence the water supply, so the extraction of water and soil water storage, and also crop demand. And so these all interact over time and to determine the water balance of the crop and the final crop development. And as with surface soils, we would have, we've got the extraction of water, which is one of the constraints, and also we will have the soil water storage. So the extraction of water is controlled by the rate and the extent that the profile is explored by the roots, and the rate and extent where the water in the zone, if the water in the zone can be used. And then we've got soil water storage, which is controlled by plant available water capacity, as well as infiltration and drainage. So when we were thinking about setting the scene conceptually, we were looking at the exploration of the soil profile by roots is described by the vertical rate of descent of those roots and the maximum rooting depth achieved. And the time to this maximum rooting depth is achieved within a growing season. And the question is there still time within this growing season, if these roots get to depth, that we are able to, the plant's able to extract some water? And if there is delay to that, that means in terms of, because of a constraint, that the root's not able to get into that water, or is the constraint meaning that the maximum depth is a lot shallower than it should be? And then once we look at the soil layer, once in the soil layer, those roots, the rate of water extraction declines with time from the drainage upper limit to the lower limit, and the rate of water extraction and the crop lower limit interact to determine the time at which that crop lower limit will be reached. So we've reviewed many papers where we were able to split up the range of interventions that can be used to improve water acquisition by plants to overcome subsoil constraints. And these were mostly in the realms of looking at improving soil structure, increasing root elongation, increasing plant available water, or improving access to the water that might be present in that layer. And the interventions are mostly grouped into either the physical interventions, which look at maybe modifying the structure of the soil, the agronomic or management interventions, looking at root elongation into the subsoil to get to that water. And then there's the plant genotypes to improve crop performance through the root strategies for root growth.
Pointed out. Oh,
Thank you. All right, so many of those in the chapters, in the sections of our chapters, we looked at the rate at which roots explore the soil profile, the maximum depth of soil exploration, the efficiency of the extraction of the water from the layer, and then also the consequence for crop water use in terms of how is it influenced by the amount and distribution of rainfall, soil type, and the depth of the soil constraint. And many of these first potentials to improve the acquisition of water by the roots are affected by overcoming soil mechanical resistance and compaction, looking at the use of cracks and soil pores and biopores and root channels for the movement of roots, and looking at the interaction of those soil pores in those with the root architecture and root traits of those plants. So there's significant understanding of some of the mechanisms by which subsoil constraints can be influence the uptake of water. And there are some avenues for further clarification and quantification of that. And that includes looking at the soil root interface. So looking at how the water is transferred from the bulk soil to the root in the subsoil and how that is in terms of the vascular tissue as well. Looking at crop management practices that might modify soil pores, because soil pores are very important for crop root systems. So it's information about pore size distribution, continuity and stability, and also quantifying the availability of water and the capacity of the crop to access that water over space and time. So that's in space and time in terms of at depth and also in your soil profile, but horizontally. Thank you.
Next one, Jim. So segue into biopores, which is a very hot topic of discussion in soils literature at present. Biopores are really quite important, particularly where you have dense or high density subsoils, because they're pathways through which roots can penetrate. And even at low density, the research suggests that these are highly significant in the acquisition of water and nutrients. And often the biopores are inhabited by successive generations of plants, not only in forest ecosystems, but also in agricultural ecosystems. But plant species differ quite a lot in the way in which they access those biopores and the resources. Also, biopores often have nutrient enrichment around them, and so there's an effect on nutrient use efficiency. So biopores, I think, is an area of subsoils, particularly where we're doing massive re-engineering of soils, as we are in Western Australia, that could be a very prospective area for research. In our review of the literature, the Australian approach to looking at water-limited yield potential seemed to be quite a unique approach to understanding what's possible with crops, particularly in rain-fed environments. And it's been a major driver of our thinking in Australian agriculture and what constraints we should try to overcome and how farmers can be guided as to what the yield potential is. It's a concept that I think internationally could be a big driver as well. One of the things that we know is that something like 20 kilograms of grain per millimetre per hectare is our target for wheat. And our good farmers are getting 75% to 80% of that. But most farmers are only getting half of that yield potential. But one of the interesting things from work that John Kierkegaard and his colleagues have shown is that a little bit of water in the subsoil late in the season can convert to at a much higher rate of grain than the overall seasonal water use. And that's one of the reasons why we have to continue to chase subsoil root penetration. The issue with a lot of our subsoils is that they have multiple constraints, not single constraints. Our research has tended to focus on one of these constraints at a time. And we know, for example, in Western Australia from the deep earth work that our shallow duplex soils, for example, many of them will have 3 or more constraints simultaneously. And there are some cautionary tales here about focusing on single constraints. A really great one is the boron toxicity story. Brian Cartwright in South Australia identified boron toxicity in the early 1980s. And that led to quite a big research program around breeding for boron toxicity tolerance in wheat and barley. When they released those varieties and tested them around, they found that they didn't perform any better than standard varieties. And that's because the soils that are high in boron usually also are high in pH, often saline, sodic and dense, maybe have micronutrient deficiencies. And so focusing on the single limiting factor, boron, really didn't achieve very much without looking at all of those constraints. Talk mostly about Australia, but one of the reasons that we thought a Brazilian-Australian partnership in this book would be a good way to go is that in both countries, a lot of our land development the southwest of Western Australia and the Cerrado region of Brazil were very constrained by subsoil constraints to develop agriculture, and overcoming those constraints was a really important part of developing agriculture in that region. In Brazil, the Cerrado region is a vast area of relatively flat land that's very suitable for mechanisation, but predominantly very acid subsoils. And without being able to treat subsoil acidity, they weren't able to grow crops productively. So they developed a technology which involves high rates of lime, 5 tonnes, mixing it to 30 centimetres by tillage, following it by a fast-growing cover crop to control erosion and to maintain soil structure, probably produce biopores, and then follow it with no-till cropping. And they also use gypsum as a way of trying to add to the amelioration of subsoil aluminium toxicity. And that technology essentially won Brazil the World Food Prize several years back for being able to bring agriculture to a very vast area of Brazil. The chapter on subsoil acidity was led by Clayton Budley, who was at La Trobe, now at Melbourne University, Murdoch University graduate. And he reviewed what's been learned about subsoil acidity and its management, reiterating what we know, that applying lime to the surface treats a layer at the surface but doesn't do much for the soil below. There's been a lot of new work on novel organic products and novel lime and gypsum products to try and increase the amelioration of subsoil acidity. But one of the things I learned from Clayton's chapter is that there's been this view that if you've got aluminium toxicity in the subsoil, breeding for tolerant varieties just buys you time, doesn't solve the problem. But that may not be the case. And the argument that Clayton puts forward is that acid subsoils will generally have anion exchange capacity. So they often do store nitrate. And if you can get roots that are tolerant of aluminium to take up that nitrate, then you get an exchange of nitrate for hydroxyl by the roots. So you may be able to get some amelioration of the acidity in the rhizosphere. Not only that, but the capacity to grow roots into those aluminium toxic subsoils releases carbon, and there's some complexation of aluminium with carbon that may also help to ameliorate conditions, possibly in biopores rather than as a mass change in the soil profile. So that to me was quite a useful new insight from that chapter. We also talked about the nitrogen cycle and how it affects the rate of acidification. And we know from a lot of research there are many key principles for trying to reduce the rate of acidification, reducing nitrate leaching risk, avoiding overuse of ammonium-based fertilizers, slowing rates of nitrification, splitting nitrogen fertilizer application, all of those things. But he argues that most of these methods of slowing down acidification are particularly useful for slowing topsoil acidification, but may not be so effective for the subsoil. And his argument is that for subsoil, we really need to be looking at low cation to anion ratios in the uptake by plant roots. And that's easier said than done. There are a few other chapters on different types of subsoil constraints. Craig Scanlon, Karen Holmes back wrote a chapter looking at soils with gravel and sandy subsoils. And Karen did some original work in trying to quantify globally the areas of soils that have subsoil constraints, and comes up with 29% of global soils having more than 15% gravel in them. And the fundamental limitation of those high gravel contents is that you get limited ability of the subsoil to store and release water and nutrients to roots. Craig also pointed out that it's important to understand in these sorts of subsoils how deep the roots can go, because if you look at cumulative plant available water content to a metre depth, you might have 55 to 105 millimetres of water storage. But if the roots can't get deeper than 30 centimetres, then you've greatly restricted the amount of storage of water there. And similarly with the sand-rich subsoils, which we've defined here as soils with less than 15% sand. They comprise about 5% of global arable soils based on Karen's analysis. They too are limited by the ability to store and release water and nutrients for plant roots. But in that range from 0 to 15% clay, there's an enormous variation in sandy soil properties. So we have lots of sands that have less than 2% clay, and other people in the world are talking about sandy soils that have 10 to 15% clay. And we know that those sands are very susceptible to compaction. You can generate under mechanised cultivation very high penetration resistance levels that restrict root growth and therefore water uptake. In Australian agriculture, there's been a move towards controlled traffic that is a partial solution to that problem, not a total solution. And also in Australia, the addition of clay and also organic matter to the subsoil has been worked on as well. I don't see a lot of that type of work happening in other parts of the world, so hopefully the book will draw attention to that. If you look at the root zone, up to 2/3 of all of the nutrients in the root zone are stored in subsoils. And under ideal conditions, if there are no constraints to root growth, very high percentages of N, P and K uptake can be coming from subsoil. And yet we're getting this shift globally towards no-till, which is stratifying nutrients closer to the surface. So that's running a little bit counter to our interest in trying to increase root exploration more deeply. One of the areas or one of the gaps that appears from Mars chapter is that we still don't know how to predict when the deep placement of nutrients in soils is likely to give responses. And this table here just illustrates, it's actually from some German work where they've quantified the contribution of subsoil to phosphorus uptake by wheat crop. And you can see that once you get past brooding stage in this particular study, significant amounts of nutrients were coming out of the subsoil. Something else that's often not well known is that for a number of nutrients, they need to be in sufficient concentration around the root tips in order to allow the root tips to continue to grow. And that applies to zinc, boron, calcium, manganese. And we know that when we're applying those micronutrients in particular, they mostly are concentrated at the surface. And the subsoil remains as low in micronutrients as the virgin soils do. And that's a possible limitation on root growth that we haven't really explored. And where you have these low levels of nutrients in the subsoil, supply in one part of the root system doesn't ensure that the roots will grow in another part of the root system where the levels are low. And we know that in many parts of Australia, there are depletion of subsoil nutrients going on. So this is work of Mike Bell in Queensland, showing quite substantial depletion of phosphorus, potassium and sulphur occurring on those heavier textured soils, and they're getting quite substantial yield responses to the deep placement of nutrients 20 centimetres into the profile there. Soil biology. Most of the soil biological activity is in the topsoil. That's where the carbon is and the oxygen supply is highest. Most of the studies on soil biology are restricted to fairly shallow depths. But we do know from many studies that soil biology goes much deeper into the profile. Mycorrhizal roots down to 1 metre of depth. There are some studies suggesting bacterial counts down to 6 metres or so, nodules to 0.5 metre depth or greater. But the chapters that looked at soil biology came up with very few studies where people had actually looked at soil biology in the subsoil. And one of the things that we should be prudent about is if we're putting a lot of effort into growing more roots in subsoil, we need to make sure that that's not going to be undermined by increasing pathogen attacks or infections of those subsoil roots. So I'd just like to now draw some conclusions from what I've learned, in particular from this book, that the existence, the prevalence and the severity of subsoil constraints globally is under-recognised and underreported. And there are many of them. Some of them are natural features of soils, and some of them are induced by land management. And even the best practice applied to topsoil is not going to get you the water limited yield potential or the potential yield of that environment if there are subsoil constraints. We know that in tropical regions there are a lot of deeply weathered regoliths, and the work that's been done in Brazil, for example, probably has a lot of flow over into many of those regions. But there are other parts of the world that have deep soils and deep regoliths with subsoil constraints, where much of the Australian examples and learning could be relevant. These deeply weathered regoliths are interesting in their own right because they're often very old and have been through many cycles of weathering, and so understanding their origin is complex. And it does appear that biology has played a really important role in the formation of properties of those regoliths. The main reason that we are concerned about subsoil constraints is that they limit water and nutrient acquisition by crops, and therefore they don't reach their full potential of the environment. And part of that is not just how deep the roots grow, but how quickly they grow into those subsoil environments. We know that if there's no constraint on root growth, they can be taking up a large proportion of their nutrients from subsoils. And our conclusion from the book is that subsoils are the new frontier. It's not that topsoils are unimportant or irrelevant, but rather we've done a lot in improving and understanding topsoils and managing them. But now there's a great opportunity to look deeper and to understand more about these subsoil constraints, where they occur and how we might ameliorate them to lift crop productivity in many parts of the world. So thank you very much.